In this video, we're going to talk about timing. Before we start with timing, of course, we're going to review the 5 things that make a spark and show you where timing fits in. We have power, right? We have to provide power coming from the ignition switch into the system. We have a trigger. There's no current carried to the trigger. That was our engine speed and position. Then we had switching. Switching is what actually turned our ignition coil primary on and off. So the switching controlled the negative side of the coil. Then we get to secondary. Our secondary, half of our ignition coil, spark plugs, plug wires, all that stuff. And then plugs. Yes, I know. If you're watching this video and maybe you haven't taken my class, you're going, well, no, the plugs are part of secondary. Well, they are. But we break it down into these 5 components to make up spark. Every car ever has these same 5 components to make up spark. We always have power of some kind. We always have some form of a trigger. We have switching, secondary, and then I call out plugs separately. The coil actually falls in halfway between the primary, which are the top 3, and the bottom 2, which make up the secondary. The coil kind of hits on both of these, but for our purposes right here, we kind of include it right in between the 2. So what we have to add in here, we actually are missing one piece. It took this to make the spark, but we have something else that's important. We have to get the spark happening at the right time, which is going to put in one more thing, and that's timing. The timing is going to go right between trigger and switching. So the trigger is usually going to something, whether it's an ignition module, a PCM, something. And then that component is going to make a decision based on other inputs, potentially. And it's going to come up with a timing decision. And based off that timing decision, that's where we're going to get switching. So now we actually have 6 things. We have 5 things to make the spark: power, trigger, switching, secondary, and plugs. And now we add timing to control when the spark happens. Okay, now, when it comes to timing, there's a reason that we have to do it. Now, normally, we're going to start somewhere about 10 degrees of crankshaft timing before the piston reaches top dead center at an idle, somewhere between 10 degrees and 0. We'll fire that spark plug, and then the mixture will ignite and it will start to burn. And it generally burns until we get between 10 and 20 degrees after top dead center on the way down the power stroke. At that point, the piston is moving downwards rapidly. This space is expanding in size rapidly, and so we're not really taking any more advantage of that energy. If we don't have our burn timed correctly, we end up just kind of chasing the piston down, and we don't transfer that power, that energy to the piston, through the crank, out to the wheels. It doesn't do us any good. It's a waste of fuel. So ideally, we always end between 10 and 20 degrees after top dead center. It varies a little bit depending on engine build and design. And some of that is simple mechanics. As our crankshaft, right here we're at a 90-degree angle on the crankshaft to center of our cylinder line. Then as we come up, now we have a different mechanical leverage here. Same thing on the way down. So some of that is simply the way that this is designed. If they offset the rod, it's a little bit different because it changes this lever. Just remember, general rules, we want to fire it so that it is completely burned out by between 10 and 20 degrees after top dead center. Now, where things change. On a stationary engine that runs at a single RPM, we could keep that constant. But we're talking about automotive applications, and these are not stationary engines, and they vary a lot. If we speed up the engine, we have to change the timing because things happen faster. When we speed this engine up, if we were firing this at close to top dead center and then by 10 degrees it was all supposed to be burnt out. Well, that's a far cry in time at 800 RPM as it is at 5,000 RPM. In the reading for this class, and I've seen in other places, it listed that it takes about 30 milliseconds to do a complete burn of our combustion gases. Well, there's a lot more variables than that. In fact, you'll find a lot of engineering won't actually give you a number like that. So be cautious using that number. The 10 to 20 degrees completion, or that it should complete by 10 to 20 degrees after top dead center, now that is accurate. The 30 milliseconds of burn time, that varies a lot. What is true is that often we have to start that burn sooner when we have a much higher RPM because we have less time. In fact, here's an example. At 800 RPM, 10 degrees before top dead center to 10 degrees after top dead center. I just did 10 to 10, a 20 degree span because it was easy math. Okay, that 20 degree span takes about 4.17 milliseconds. Takes 4.17 milliseconds to travel that 20 degrees at 800 RPM. But if we get on it, if we speed this up to 5,000 RPM, now that same 20 degree span from 10 degrees before top dead to 10 degrees after takes just 67 hundredths of a millisecond. That's how much we sped that up. So the other thing we have to talk about too is load. I've mentioned load before. Load is a concept. Load is not just one thing. We don't have a failed load in our engine and have to replace it. Load is the amount of work we're asking the engine to do relative to its power output at that point in time. So the load on an engine at an idle could be excessive by simply turning on air conditioning and turning the power steering all the way one direction. The load driving down the freeway. If we're driving down I-5 at 2,500 RPM in fourth gear on a flat stretch of I-5, that is a completely different load than driving up Mount Hood in fourth gear at 2,500 RPM. It's a different load. We're asking the engine to do a different amount of work. Now that comes into play because when we increase load, we increase cylinder pressure. In fact, it turns out that any time we increase cylinder pressure, whether it's through load, whether we add boost, no matter what we do, if we increase cylinder pressure, we actually have to back the timing off a little bit. If we're coming up normally, and say we're going to ignite this at 20 degrees before top dead center. It comes up, it ignites, we're still moving forward, we're still compressing, even as it's igniting and burning. We get a nice even burn. It finishes by 10 degrees after we put lots of force on the piston. Now, we up our boost. Pressure's much higher in here. Piston's coming up, we ignite the spark plug, fires off, but now the pressure's so high that we have pre-ignition or auto-ignition. It doesn't have a nice propagation or burning of the flame front, it just explodes. So that means that in that application, that higher pressure application, we have to actually set the timing back so it occurs later. We already have a lot of pressure in there, so we set the timing back later, and that helps to make sure that we don't have that pre-ignition or auto-ignition, and we have a good burn without that. When we talk about things like pre-ignition and detonation, which is a subject for a different video, what you need to know is that the pre-ignition is extremely damaging. If that goes off and essentially explodes as this is still coming up and building pressure, that easily burns hole screw pistons, collapses ring lands, does lots of damage. We don't want that to occur. So we have to set the timing anytime we have a higher cylinder pressure to compensate for that. Now there's other things we can do. We'll discuss those in the future, but that's just one thing we have to be aware of. Any increase in cylinder pressure, timing has to back off or less advanced. Very rarely do we time an engine after top dead center, which we would term as retarding the ignition timing. Anytime we take the ignition timing back from where it is. That's retarding the timing. See the terms video. Anytime we build extra pressure, we have to back the timing off. Here's a fact though. If we can maximize our timing under load when we're making power, if we can set that timing to 30 to 40 degrees advance, 30 to 40 degrees before top dead center, where we're making power, many studies and papers have been devoted to finding the perfect timing, and often they agree that if you can get it to that 30 to 40 degrees before top dead center when you're making your most power, that's when it runs right. That's when you're going to make the top power. That's when it's super efficient. Things are good there, just so long as we're not pre-igniting or detonating. So then we have other things to take into consideration. Also things like EGR, exhaust gas recirculation. That actually cools the cylinder off. That helps reduce the pressure. You can actually increase the timing then. So that's something that actually helps us. EGR is something we'll discuss when we get into emission systems. When it comes to actually moving that timing, I mean, now everything's computer controlled. The PCM has a variety of factors it looks at: speed, position, load. We have some inputs specifically for timing. And it uses those to help determine the proper timing, but that's not how it started out. Back in the early days, say Model Ts and all those old cars, you actually set the timing yourself. There was a knob that you pulled out or pushed in on the dash to change the timing, and you manually set that timing as you drove the car. It had one setting to start, another while you were cruising. You moved that timing around manually. Then we went to vacuum modulated timing. So now we're going to use engine vacuum, because as you find, vacuum is related directly to load. So it's great for any place we need to measure the load on an engine. So we had our vacuum diaphragm on the distributor, where a change in load through vacuum would cause a change in timing. If we had less load, we tended to run a little more advance. With more load, we ran less advance. And that was just simply done through using the engine's vacuum on a diaphragm. Of course, then we get into the era of the ignition control module, but really before computers really took over. And in those situations, oftentimes our ignition control module would have a preset curve, timing curve in it, so it would give a different advance at different RPMs. Not so much tied into load, so that was all in how that ICM was engineered. Now it's all PCM, so we can do a very accurate job and maximize our ignition timing's abilities. We'll talk a little bit more about that in the NOx sensor video. So timing, we need to have it, because as we change speed, as we change load, as other factors change, it changes the amount of time and other factors inside that cylinder, so we need to change when that spark plug ignites. If this was just a stationary engine, we wouldn't have to do that. So we have to change it. Now it's just up to the PCM. The why we change it, again, speed of the engine, load on the engine, design of the engine, additions to the engine, i.e. forced induction, nitrous, those other kinds of things. So timing is important. Your base rules of thumb, remember that 30 milliseconds of the reading, we're not really going to go with that. Know that that varies a lot. However, the fact that you need to finish up your burn by 10 to 20 degrees after top dead center, that is extremely accurate. And with that said, and that extra knowledge, we'll catch you in the next video.